Well, we're going to take a break from chemistry for just one movie and start talking about light. Concept with which, of course, you're very familiar. Concept that can get complicated very, very quickly. We're not going to get it very complicated very quickly at all. We're just going to look at the real fundamentals of it. First fundamental is that light is, of course, a form of energy. In particular, and we'll use this phrase several times, it's electromagnetic radiation. There are different types of electromagnetic radiation which we can treat all under the same umbrella of light. You don't have to worry too much about what we're going with this electromagnetic radiation. Essentially, you have light travels in waves. We can think of it as a wave of electrical energy, and in perpendicular to it a wave of magnetic energy. And I'm sure any physicists who heard that would start slapping their heads and rolling around and sharpening their knives and so forth. So anyway, there is the wave. That's kind of a pretty wave, isn't it? And so we think of that as being how light travels. Now we need to understand certain components of a wave, so we'll draw a line that hopefully goes right through the middle of it. Now, if we join one point on that line to its equivalent point, that is called the wavelength. So I could have said the wavelength is the distance between this peak and this peak. I could have gone between the trough and the trough. I could have said coming halfway down here, so going halfway down there. I could have said crossing the origin as you go from above to below, going along to crossing the origin as you go from above to below. The distance between equivalent points is called the wavelength, and the funny little symbol we use for this is a Greek lambda, right? Greek L for length, so lambda. Anytime you see that, it's the wavelength. And of course, the default units of wavelength, of length, are meters. Although, as we'll see, we'll typically use some of those different types of meters, like nanometers and millimeters and micrometers and so forth. Another part of the wave here is called the amplitude. You can think of that as being the height of the wave, and for light that's related to the intensity of light. So if you have a much brighter red light, for example, then what happens is that the wave is just much higher. So instead of being like that, it might be going up, down, and then down further and up further, and so on. As chemists, we're interested in the wavelength, not so much the amplitude, but we're extremely interested in the frequency of a light wave. Now, frequency is sort of a tough one. It's the number of cycles per second, which we can call 1/second or per second, and we can summarize the whole thing as a hertz or Hz. So you see Hz, it means per second, or number of wavelengths per second. So essentially, if you stand in a spot and you watch the wave go by, it's how many wavelengths are you going to see in a second. Now, frequency and wavelength are related to the speed of a wave. Okay, and the best way I think I can do this as a PowerPoint is just to draw a different wave, and let's compare these two waves. Okay, now when you look at them, let's just say X and Y. X are the starting points, and Y here is after we've done one wavelength of this first wave. Okay, now how does the second wave relate? Well, obviously, when you look at the second wave, I hope you can see, first of all, that it has a much shorter wavelength. Okay, the wavelength here is going from there to there. It's much shorter than the wavelength going from there to there. Okay, so we've got a much shorter wavelength. But now, if you were to say that this wave, both of them, have the same speed, so as you go from, say, X to Y, it takes 1 second. Well, here then, you've got 1 wavelength per second. Here you've got 3 wavelengths per second. Okay, because from X to Y is 1 wavelength here, and it's 1, 2, 3 wavelengths there. Okay, so as we decrease the wavelength, we're going to increase the frequency. Okay, as long as we've got some nice measure, in this case the distance between X and Y. So the speed of the light, or the speed of this wave, will be you got from X to Y in 1 second. Here it takes you 1 wavelength to do that. Here it takes you 1, 2, 3 wavelengths to do it, which means that you must have 1 wavelength per second here, 3 wavelengths per second here, because the wavelength here is 1/3 of the wavelength there. Okay. Now that was a sort of hand wavy thing. Hopefully it made some sense to you. We can also get this relationship associated with the speed by thinking about it in terms of units. Speed is meters per second, which is meters times 1/seconds. And what's measured in meters is the wavelength. What's measured in 1/seconds is the frequency. So the speed of any wave is the wavelength, right? How long that wave is multiplied by the frequency, how many of those waves pass. Okay? Now, when we're talking about light, all light has the same speed, called very unimaginatively the speed of light. Somewhat more imaginatively, the symbol used for the speed of light is c, which comes from the Latin word celeritas for speed. So that's a little bit better, a little bit more imaginative there. And the value of c, 3 times 10 to the 8 meters per second, actually 2.998 times 10 to the 8 meters per second, but in this class we'll live with it being 3 times 10 to the 8. So therefore, any type of light, c, the speed of light, is the wavelength of that light times the frequency, or as the frequency goes up, the wavelength goes down. So we see that here. Okay, here we've got the wavelength from this first wave to the second wave. The wavelength is increasing, which means the frequency is increasing. Throughout the whole course, you're going to need to be very, very familiar with the electromagnetic spectrum, otherwise known as the types of electromagnetic radiation and the types of light. And you not only need to know the types of light, you need to know them in order of increasing wavelength, order of decreasing frequency, which is of course the same order. And you also need to have an idea of approximately which wavelengths and which frequencies correspond to which types of light. So this slide, the picture that's going to be on this slide, is something that we want you to be familiar with. You'll actually get given it on our periodic tables that we hand out for exams, but it's much nicer in class if you can be familiar with everything that's on this. So anyway, I'm going to have two axes, one showing frequency, one showing wavelength. Now, because all light has the same speed, that means that as the wavelength gets bigger, the frequency gets smaller. And that's what you're seeing on these graphs here. The bottom axis is wavelength, and it's getting bigger from left to right. So 10 to the minus 16, minus 14, blah, 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 all the way up to 10 to the 8 meters. So really high wavelengths, really teeny wavelengths. Now, if you look up here on the frequency starts off high and gets much smaller. So wavelength on these axes is increasing from left to right, frequency is decreasing from left to right, because as frequency changes, wavelength changes in the opposite directions. Now, the really high wavelength or low frequency electromagnetic radiation are radio waves and TV waves. Okay, so when you have your radio waves, these are all up here at these high wavelengths, high frequencies. So for example, many of your favorite radio shows broadcast at such and such megahertz. Well, 1 megahertz is 10 to the 6 hertz. So this is where your favorite radio stations are broadcasting. TV stations, even lower frequency, higher wavelength. Now there's a sort of division here, it's an artificial division where we go from radio waves to microwaves. Now of course microwaves don't just exist in ovens, but they're also what carries your voice when you're having cell phone conversations. So very, very important to your life. Microwaves, higher frequency than radio waves, smaller wavelength than radio waves. After microwaves is infrared. Now, of course, back in my day of school, nobody knew about infrared at all. Now, of course, you've seen all these infrared beams, infrared goggles, and so forth. Those just enable you to see in the infrared, which has a frequency between about 10 to the 12, 10 to the 14, and wavelengths down here from sort of sub-millimeters to micrometers. Now, the next part of the spectrum is, of course, the most important for you in your day-to-day lives. It is the visible spectrum, which I've drawn here, going red, orange, yellow, green, blue, and violet. And you can see that this occupies a very, very small part of the spectrum. Okay, our eyes not very good at all. They can just pick up this teeny, teeny, teeny part of the spectrum. Now, even smaller wavelength or higher frequency than the visible spectrum, you have ultraviolet rays. And then even higher frequency, lower energy, lower wavelength are the X-rays, and then a little dotted line up here separating X-rays artificially from the gamma rays. Pretty much it's a continuous spectrum, so high energy X-rays are sometimes called gamma rays, low frequency gamma rays are sometimes called X-rays. So gamma rays up here, really high frequency, really small wavelength. Okay, and something that we will touch on the next slide, next two slides actually, is something that I kind of gave away here. That radio waves, not very much energy at all. Microwaves, a little bit more energy, but on the other hand, just imagine if you were holding your cell phone and the energy of the signal was the same as the energy of X-rays, you would very quickly have a very sore ear until it was burned off. Okay, infrared, even more energy. Ultraviolet, of course, the light that comes from the sun that gives you a nice tan and then ultimately burns you. X-rays, when you go even to a dentist's office and they turn on the X-rays, the dental hygienist and the dentist run out of the room before they do it because they're very high energy. And then of course gamma rays, much high energy at all. So I'm going to spoil the surprise a little bit and point out that the energy associated with different types of electromagnetic radiation increases as the frequency increases or as the wavelength decreases. So very high energy, very high frequency, very low wavelength. Now, this is of course the important bit that you need to be familiar with, and so we'll spread it out a little bit. Here's a much prettier expanded view of the spectrum. And its wavelength here is in the hundreds of nanometers. Now, a nanometer is 10 to the minus 9, so 100 nanometer is 10 to the minus 7. So these here, you got 4, 5, 6, 7 times 10 to the minus 7. Notice that the violet light is the smallest wavelength, which means, of course, it's the highest frequency. Red light has got the highest wavelength, which means it has the lowest frequency. And I do want you to be kind of familiar with these, right? So the violet starts here at about 385, 390 nanometers. And so when you see something 400 nanometers, you know it's purple. When it's about 450, it's blue. 500, that sort of bluey green region. 520, 530, and your greens up here at about 580, yellow, and then moving into orange, and then the big red area from about 630 or 640 up until the really dark reds at about 740. So be familiar with what this spectrum is showing you with the different wavelengths associated with the different, first of all, types of the visible spectrum, and then the wavelengths and frequencies associated with the other parts of the spectrum. So I provided a little spoiler on that last slide talking about the energy of light. And we're not going to go into huge depths about it, but something that had been puzzling scientists for several hundred years was an anomaly associated with light, waves, and energy. Normal waves, their energy is associated with the amplitude. If you think of the bathtub, okay, if you slap the water in a bathtub, so you provide some energy, you make a wave. Okay, that energy that you've put in is transmitted away, is carried away in the waves. If you slap the water harder, then you're going to have a higher wave. More energy, more amplitude. On the other hand, the amplitude of light is associated with the intensity of it, not of the energy. The energy of light is associated with the frequency. So you can have it really intense red light, and it's a higher amplitude, but it's the same wavelength, it's the same frequency as a much less intense red light. And it's not very energetic. But on the other hand, you take an X-ray, even at very low intensity X-ray, it's still got very high energy. Now, there are two great scientists who contributed to trying to explain this. First one, Max Planck, and the second one, Albert Einstein. Planck recognized that there was a relationship between the energy of light and the frequency, just what we saw on that last slide in a qualitative sense. Okay, and that relationship is proportional. Energy is equal to h, some constant that is called the Planck constant, and this is its value here, multiplied by the frequency. So increase the frequency, increase the energy. Okay, now this was explained better by Einstein, because Planck came up with a relationship, but he didn't really say what does it relate to, other than maybe this means that light energy travels in a form of little packets called photons. Okay, now I want to help you visualize these photons in two ways. The first way is just to illustrate what a nerd I am, and that is by pulling up Star Trek. Okay, I don't talk about, you know, the make-up takeover series, right? But the original series from the 1960s, that is of course the really good subject of these fantastic recent movies, what, 2012, 2010, something like that. Anyway, the recent movies that have come out with the Enterprise. Now of course the Enterprise's great enemies were the Klingons, so here's a pseudo Klingon ship here. So as soon as the captain, James T. Kirk, sees the Klingons, he says, let's fire our phasers at these Klingons. And so what you would see is you would see a beam of light energy coming out from the Enterprise to shoot the poor little Klingon. Okay, and that was of course thinking that light is this solid beam, these waves. Okay, however, there was also another weapon that Kirk could use on the Klingons, and that was the so-called Photon Torpedoes. So here comes the Klingon ship's buddy ship, right, all sad and so on, that their first Klingons have all been annihilated. And so Kirk says, let's not mess around with lasers these times, let's use the Photon Torpedoes. Now what that looked like was, instead of a solid beam of light, as if the light's traveling in waves, was these little packets of light hitting the poor little Klingon. So each one of these is a photon, is a little packet of light energy. Now of course you can kind of think about it, well, if these photons are traveling fast enough, then they would blur together and you would get the appearance of that wave, of that nice little beam. Another illustration, and one that I prefer, comes from thinking about Albert Einstein's explanation of the photoelectric effect. Something that a lot of people find peculiar is Einstein. Of course, everyone's heard of him, called the greatest scientist of the 20th century. He only won one Nobel Prize, and he didn't win that Nobel Prize for relativity. He won it for this, for his explanation of the photoelectric effect. Now, the photoelectric effect was a fairly well-known phenomenon by this stage. We're talking about the start of the 20th century. Now, if you take a sheet of metal and you shine light on it, then if that light is the right type of light, then it will shoot out a beam of electrons. So in other words, you're turning light energy into electrical energy, and also, as we'll see, kinetic energy for those electrons to move. Now, making up some numbers here, if you come along with just red light of any intensity at all, you don't get any electrons coming out of it. Okay, if on the other hand you shine green light, for example, with low intensity, then you get some electrons getting released, and they have not just the energy required to get them away from the surface, but they have a particular kinetic energy, which we'll call kinetic energy 1. If you turn up the intensity of the green light, you get more electrons coming out with the same kinetic energy. Blue light, which of course now we know blue light has got a higher energy, even if you have it with low intensity, you'll still get electrons, and those electrons will have kinetic energy 2, and their kinetic energy is greater than the kinetic energy of the electrons released by green light. Turn up the intensity of the blue light, you'll get more electrons coming off, and they have the same kinetic energy as from the low intensity light, that is bigger kinetic energy than that from the green light. Okay, now Einstein's model of this was to say, let's not think of this as light in waves, but let's think of that light energy as coming in little packets of energy, these photons. So we're thinking of it as we're beaming photons at it, and we're releasing electrons. Okay, now if we think of, first of all, a red light photon, it's not much energy. Red light isn't very high frequency, not much energy. So let's think of that as throwing a ping pong ball at a pool ball or a snooker ball on a table. Let's talk about pool balls, shall we? Okay. If you have a pool ball on a table and you throw a ping pong ball at it, nothing's going to happen at all. That ping pong ball doesn't have enough energy, enough momentum to make the pool ball move. But on the other hand, if we now increase the momentum, increase the energy of our so-called photon, and we say throw a baseball at it. Okay, well, a baseball, you throw a baseball at a pool ball and it's going to have enough energy, enough momentum to release that pool ball from the table and start it moving with a particular amount of kinetic energy. But if you have more pool balls and you start throwing more baseballs at them, then you're going to get more pool balls moving, but they're going to have that same amount of kinetic energy. Okay, so the ping pong ball, not enough energy to release the electrons. The baseball, enough energy to release the electrons and give them more kinetic energy. Now let's throw something with even more energy than a baseball. Let's throw a cannonball at our pool ball. Well, that cannonball is not just going to make the pool ball move, it's going to make it move much faster, give it much more kinetic energy. And again, if you fire more cannonballs at the pool table, then you'll release more pool balls that will have the same kinetic energy as with just the one cannonball. So the way that this was explained in fancier terms is that the energy that is coming in from the photon, right, Planck's constant times the frequency, is equal to a binding energy that's required to make electrons leave the metal plus the kinetic energy. So you have a total amount of energy coming in, some of that energy is needed to release the electron, and the rest of it goes into making the electron move. Okay? If the energy that you're putting in is less than the binding energy, as was the case, for example, with the red light, you're not getting any electrons because the energy of the light coming in is not enough to overcome the binding energy. So the photoelectric effect, the best explanation of it is to say that light energy travels in little packets of energy in these photons. That photon, in order to release an electron, has to have a certain minimum energy, a threshold energy, to overcome the binding energy that's holding the electron to the metal. If it's got enough for that, as we had with our green light or our blue light here, well, then it will release the electron and give it a certain amount of kinetic energy depending on how much energy is left. Green light and blue light. Blue light's got more energy, and so therefore the binding energy required to remove the electron will be the same whether you have green light or blue light. So there'll be more light energy left over when you use the blue light, thus you have more kinetic energy for the electrons. Okay, that's really the end of our physics discussion. Hope it made some sense. I'll be back applying it to chemistry.